Alright, in the last video we talked about matrix addition and scalar multiplication, and we defined matrix multiplication. Now let's take a look at some properties of these operations. So, properties of matrix algebra. So the first property is this theorem, which is that if you have if you have three matrices, A, B, and C, and you can multiply them, if you do A times B times C, that's the same as taking the matrix AB and multiplying by C. And you can check that in a bunch of examples that this is true. If you come up with some matrices A, B, and C, and if you do B times C first, and then do A times that matrix, you're going to get the same thing as if you did A times B first, and then multiply that by C. So there are a couple ways to see why this is true, and one way is to see what these matrices, if you think of them as transformations, to think of what they do when you apply these transformations to a vector x. So if you take these matrices and multiply them by the vector x, what do you get? So let's check that if I take the matrix on the left, which is A times BC, if I multiply that by a vector x, I get the same as what I get when I take AB times C and then multiply that by x. So this matrix times x is the same thing as this matrix times x. If it's true that I have these two matrices and they do the same thing to every vector x, then the two matrices have to be the same. Okay. And the reason why that's true is because for instance, they're going to do the same thing to each of the standard basis vectors, so you get the same columns, right? And if you have two matrices that have the same columns, they have to be the same matrix. Okay, so we need to check that these are the same. So let's calculate the thing on the left. So that's A times BC times the vector x. Well, by definition, so I have this matrix A, and then I have this matrix BC. And so I have a product of these two matrices. If you multiply that by x, we remember by the definition of the product, so by definition of the product of A and BC, that is the same as taking the matrix BC, multiplying it by x, and then multiplying the result by A. So I'm going to write it like this. A times the vector BC times x. So this is by definition of the product A times the matrix BC. Now the right-hand side is, okay, so I have this BC times x, right? I have this matrix BC times x. That itself is a product of two matrices. So by the definition of the matrix product again, that's going to be the same as taking B and multiplying it by the vector C times x. So this is by definition of the matrix product B times C. Okay, now this is equal to, so what I have now is A, let's see here, times B times the vector Cx. And that's the same as taking the matrix AB and multiplying that by the vector Cx. So this is by definition of A times B. Right? I have this I have this vector Cx. When I do b times it, and then a times the result, that composition is the same as taking the matrix AB and multiplying it by that same vector. Okay. So that's why those two are equal. And now this is, by definition, okay, I have this matrix AB and this matrix C. When I do that product, AB times C, what it does to the vector X is, by definition, you take C times X and then apply the matrix AB to it. So this, by definition of AB times C, is equal to AB C, this product of the two matrices, times X. Okay, so let's just review why that's true. Because I have, where is it? Yeah, I have this. Because of this. And that last step that I was showing, I had something of this form on the right, and then I'm saying that's equal to the thing on the left. Remember, these two are equal, so you can go from left to right, you can go from right to left. And I'm going from right to left. Okay, to go from here to here. And now what do we have? We have that this matrix times X is the same as this matrix times X. And X was arbitrary. X was just a random vector, right? There was nothing special about X. So you know that these two matrices do the same thing to every vector X, and therefore they're the same. So since X was arbitrary, we conclude that the matrices A times BC and AB times C are equal. And that's the proof. That's a proof of the theorem. So this is the associativity of matrix multiplication. This theorem is saying that matrix multiplication is associative. That's actually one proof of this theorem. We can also think about this in terms of the functions, in terms of the linear maps that are defined by these matrices. We did that a little bit in this proof, but let's take another proof that really emphasizes the associativity of functions composition. Because we know that function composition is associative, and one way to think about this statement is we're thinking of, okay, this matrix multiplication is associative, but if we think about it in terms of composition of linear transformations, and we know that function composition is associative, that will lead to a second proof. So that's the one I'm about to show. So it's the same general concept as the first one. You take the matrix A times BC times X, and that by definition of the connection between the linear transformation and the matrix, that's the same as taking, T, the transformation of this matrix times X, okay? And this, I have a product of A and BC. And so I can apply that fact that we have, this fact, when you have a product of two matrices, it turns, the transformation corresponds to the transformation, that's the composition of these two. So if you apply that to here, I have a product, I have this matrix times that matrix. So this is going to be T sub A composed with T sub BC of X. And that by definition of the composition of functions that's t sub a of t sub bc of x. Okay. And now t sub bc of x, again, I have a product of two matrices, and so I can write that as a composition. That's going to be t sub a of t sub bc of x is equal to t sub b of t sub c of x. Okay, so the result of taking this matrix A times BC and applying it to X is equal to this. You apply T sub C, then T sub B, then T sub A. Well, we'll show that that's the same as what you get if you take the product AB times C applied to X. Because this is equal, by definition, this is equal to T sub AB times C of X. Again, that's using the connection between matrix multiplication and linear transformations. And again, I have a product of these two vectors, these two matrices. And so this is going to be T sub AB composed with TC of X. But now T sub AB, again, I have a product of two matrices, and so that's going to be T sub A composed with T sub B. Okay, so it's this composed with T sub C of X. And that, by definition, is going to be T sub A of T sub B of T sub C of X. And now you see that I have the same thing, right? These two are the same. So what that shows is that the result of taking this matrix and multiplying it by x is the same as the result of taking that matrix and applying it to x, because they're both equal to this. Therefore, these two matrices that I underline in purple, they're the same matrix. So since, let me just zoom out a bit. Again, since x is arbitrary, the first matrix is equal to the second matrix. Okay, so that's the associativity of matrix multiplication. So you can think about it in one of two ways. They're pretty related, though, this first proof and the second proof. I mean, the point is to think about what happens when you multiply these matrices by a vector x and check that you get the same thing. Okay, so that's one property. The matrix multiplication is associative. Now let's look at some other properties. So one of them is this distributive property, which is that if you take A times the sum B plus C, that's the same as AB plus AC. So you can distribute the A across when you do matrix multiplication. That's basically what it says. And then the second one is similar, that if you do A plus B and then multiply by C, that's the same as AC plus BC. So this is called the distributive property, distributivity of matrix multiplication. So I guess you could distribute the I guess it would be like this, AC plus BC. Okay, and maybe we should give some indication of why this is true. So for the first one, if you have a matrix A, okay, and then you have these two matrices B plus C, I mean, what's going on is B plus C, okay, B plus C is this matrix, And let's just call the columns of B BI's, and let's just call the columns of C the CI's. So if you take B plus C, the first column is B1 plus C1, the second column is B2 plus C2, all the way to B, say, N plus Cn, right? I have these columns. And if I multiply this matrix A by this matrix, remember what I'm doing is I'm multiplying the matrix by each column separately. So these columns I'm thinking of like separate things, and I'm taking the matrix and multiplying it by each column. So the result is going to be the matrix where the first column is A times B1 plus C1, the second column is A times B2 plus C2, and oops, no, not plus, and so on until I get to A times Bn plus Cn. But I know that, so right now I have a matrix. Each of these columns is a matrix times a vector. It's a sum of vectors, and I can distribute the matrix multiplication, right? Because I know that if I have a matrix times a sum of two vectors, I can multiply the matrix by the vector separately and then add them. So this is going to be equal to A times B1 plus A times C1 all the way to A times Bn plus A times Cn. That's going to be the last column. And I know that that's equal, of course, to this matrix where the first column is AB1, the last column is ABN, plus the matrix whose first column is AC1 and the last column is ACN. Okay, and then this matrix on the left is equal to A times B, and then the matrix on the right is A times C. Okay, so this is going to be, this matrix I started out with was A times B plus C. So that's basically the reason why this is true, that this matrix is the same as this matrix. And that's the proof of the first property, and then the second property is similar. It's the second one basically just boils down. So this is the first one, and then the second one, if I have A plus B times this matrix C1 to Cn, then I know that if I take A plus B, these matrices, I add them and multiply them by Ci, it's the same as if I take A times Ci plus B times Ci. That's a property you can probably just check directly, right? I mean, if you have two matrices and you add them and then multiply by a vector, yeah, why is that true? Okay, let's just check that that's true. So, well, if we take for granted that this is true, do you see why we get the statement? Because since this is true, then we see that A plus B times this matrix whose columns are C1 through Cn, that's going to be equal to A times the matrix whose columns are C1 through Cn plus B times the matrix whose columns are C1 to Cn. Because if you just look at the ith column, on the left, you're going to get A plus B in parentheses times Ci. On the right, you're going to get A times Ci plus B times Ci. But this is the same as saying that A plus B times C, this matrix is C, this matrix is C, right? This is the same as A plus B times C is equal to AC plus BC. Okay, so let's just check that when you take the sum of two matrices and multiply by a vector, you can multiply each matrix by the vector and add them. It's because, well, hopefully that's completely believable, but okay, let's say that the columns of A are A1 through AN, and the columns of B are B1 through Bn. So this resulting matrix is A plus B. If I multiply that by the vector x1, xn, so that's the vector x, then what I'm going to get is, well, first of all, this is saying I add the matrices first. So this is going to be A1 plus B1, that's the first column, and then the last column is AN plus BN, and then I multiply this matrix by the vector x1 through xn. Now, by definition of the matrix vector multiplication, this is x1 times, so the scalar x1 times the vector. It's the scalar x1 times the vector a1 plus b1 plus dot 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 plus xn times the vector an plus bn. So I get this vector, and then I can distribute. I have a scalar, right? This scalar, this xi, times this vector, ai plus bi. That's a sum of two vectors. I can distribute the scalar across, and so I get x1 a1 plus x1 b1 plus dot 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 plus xn an plus xn bn. And then that's the same as x1. I can factor out the x1. I'm going to get x1 a1 plus, is that what I want to do? Let me think. I have to, oh yeah, I can write it as x1 a1 plus x2 a2 plus dot 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 plus xn an. So this vector plus the vector x1 b1 plus x2 b2 plus dot 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 plus xn bn. And then the left-hand vector, this vector, is equal to the, if I take this matrix whose columns are a1 through an and multiply it by the vector x1 to xn, okay? And then this second vector is what I get if I take the matrix whose columns are b1 through bn and multiply by the vector x1 to xn. So then this left-hand side, this term, that's just a times x, and that's just b times x. So I started out with this thing, which is equal to a plus b times x, and I showed that this is equal to this, right? So that's very typical of a proof-based class. Okay, we won't be doing much of this, but I just wanted to show that it really is just multiplying the things out and checking that you get the same thing. Okay. Okay. One slightly interesting thing before going on is that, in the previous one, if you thought about matrix multiplication as composition of functions, this fact kind of just falls out of the associativity of composition of functions. If you look at proof 2, basically all we used was the associativity of function composition. But if you look at this theorem and translate it into thinking about it in terms of functions, the first one's actually a general fact about, no, let me think. Now, the second one is actually a general fact about functions. This one can be thought of as a general fact about functions. But this one cannot be thought of as a general fact about functions. Because, for instance, if you think of, like in general, it's not true that if you do f composed with g plus h of x, that in general is not the same as f of g of x plus f of h of x. Okay, that's just not true in general. If you have something like g of x equals x, h of x equals x, and f of x equals x squared, you can check that the left-hand side is not equal to the right-hand side. So somehow the fact that this first statement is true is very particular to matrix multiplication. Okay, it's not just a general fact about functions. Whereas this one, if you thought about it, this first theorem, the associativity, really can be thought of as a general fact about functions. Okay. And I'll let you think about how this second one is a general fact about functions. Okay, I don't want to get into that. Okay, so let's close with a few more facts about more properties of matrix multiplication. And the last one is pretty easy. It's just if you have a scalar times a product, you can multiply it any which way you want. It's going to be, you can multiply the scalar by the first matrix and then multiply that by b, or you can take a and then multiply the scalar by b. Okay? And then some things to note is that, so it's like a warning, that matrix multiplication is not the same. It doesn't work exactly the same as multiplication of numbers. So in general, AB might not be equal, it might not equal BA. We saw an example before where one of them was defined, but the other one wasn't. But even if they were both defined, they might not be equal. And it's actually pretty easy to just come up with an example. So an example, if you take A to just be like 1, 2, 3, 4, B to be 5, 6, 7, 8, I'm writing them as rows. If you multiply AB, you just won't get the same as BA. Okay, you can just check. And if you think about the matrix multiplication in terms of composition of functions, it actually makes sense that you wouldn't get the same thing. Because if you do B first and then A, that's different than doing A first and then B. Okay, and then another, so that's one of them. And then another one is you could have things where you get the vector 0. So if you have something like A equals 1, 2, 3, 6, and B equals -4, 6, 2, -3, you can check that A times B is actually the 0 matrix. So that's a different thing than you might be used to with numbers, right? If you have two real numbers, you multiply them, you get 0. One of them has to be 0. But for matrices, you can have two matrices that are not the 0 matrix, but when you multiply them, you do get the 0 matrix. So you do have to be a bit careful with certain matrices. We'll talk about invertible matrices. If you only work with invertible matrices, this isn't an issue. But just in general, it is an issue. And another thing is that you can't necessarily cancel. So if A times C equals B times C, A might not necessarily be equal to B. So A might not equal B. And we can actually just use the example that we had before. So if you take A to be this, and C to be okay, here's an extreme example. Let's just take C to be the zero matrix. Okay, then this is equal to B times the zero matrix. You can check that you just get the zero matrix, but A and B are not the same. So that's A, that's C, that's B, that's C. You can check that AC equals BC because it's just all zeros, but A is obviously not equal to B. Okay, maybe I only have a little bit left for this section, but I think I'll just make a different video. So all we have left is to talk about transposes of a matrix, upper triangular matrices, lower triangular matrices, and then that's it for the section on matrix algebra. So what did we do today? The reason why this video is a bit longer is because we actually wrote down proofs, which we usually won't do very much. But the first one is the matrix multiplication is associative. The second one is this distributive property. And the third one, okay, the third one, I don't even know what it's called. I guess this is like a distributive property. I don't know. And then these warnings, right? AB might not be equal to BA. So what does that say in terms of, one way to phrase it is that matrix multiplication is not commutative. Now, sometimes A times B is equal to B times A, but what I'm saying is that A times B isn't always equal to B times A. And you can get, if the second one is if AB is equal to the zero matrix, A or B might not be zero. A and B might not be the zero matrix. So that's kind of unusual. And then the last one is if AC is equal to BC, A might not equal to B. So you can't necessarily just, divide both sides. I mean, you don't have matrix division. When we talk about inverses, we'll see that if C is invertible, you can multiply both sides on the right by C inverse, and then you can get that A is equal to B. Okay, but just as a general fact about matrices, it's not true. All right, so I'll finish off in the next video. Thanks for watching.